The vertical line test is a graphical way of determining whether a function or a relation is a function or not. So in the two graphs that you see below, A and B, let's go ahead and apply the vertical line test. So if you remember the vertical line test, it said that if you had, imagine you had a pencil, and if that pencil passed through the graph from left to right, if at any one moment in time that pencil touches the graph at more than one point, it's not a function. So here, because at any one moment in time it only touches a single point on the graph, we would say yes, this is a function, as opposed to if we pass the graph through B, we see that the line would hit at more than one point, so therefore this is not a function. And the reason why is if you think of that coordinate point, let's imagine that the x value is negative, that the x value is negative 2. And if that y value is positive 3, and this y value is negative 3, we see that the x values are the same for those two coordinate points. So therefore, by that definition, this is not a function. Another topic of discussion I'd like to talk about is what makes an ordered pair or a coordinate point a solution to an equation. So if you're given an equation, say y equals 2x minus 7, in this example, if you can make a correction and say for the coordinate point 2, 3 right here that they have, can you go ahead and change that to negative 3? And in this example, it says 2, negative 3 is a solution. Well, how do we show that it's a solution? We can plug the y coordinate in as negative 3, the x coordinate in as positive 2, and simplify from there. Negative 3 equals 4 minus 7, which does simplify to be negative 3. So if that equation is true, we can make that conclusion that 2, negative 3 is the solution to that equation. So another vocab word that's review is independent versus dependent variable. Your independent variable is your x normally, typically, and that's the input variable. This is in contrast to the dependent variable, which is your y. And in most equations that you see, y is dependent on the x value. So if you look at your linear equation above, y equals 2x minus 7, the y value will vary depending on what you plug in for x. So therefore, x is your independent variable, y is your dependent variable. A linear function, which is what we're going to focus on in the next few videos, is typically the most common equation that you would probably associate with a linear equation is the slope-intercept form. It's of the form y equals mx plus b, and we will review in more detail this form. We'll just talk here about function notation, and we are doing a super quick review here, so if you have any questions, please feel free to ask during class or email me. So slope-intercept form, y equals mx plus b, can be written in function notation if we simply replace y with f of x. So the f of x part is, I always tell my students, it's just a fancy way of saying y. And the advantages of having f of x is that if we're asked to evaluate a function like f of 2 that you see down here, let's go ahead and do this problem. It tells us what to plug in for x. So this is your input value, 2, and it just means take that 2 and plug it in for x on the right. So when we do that, we get an expression on the right that we would then simplify all the way down and say that that's our y value that corresponds to an input of 2. So our output would therefore be PEMDAS. You would square first, so 4 times 2, 8 minus 3, 5. So the coordinate point is 2, 5. The y value when we're asked to find f of 2 is 5. Find f of negative 1. Can I have you go ahead and do 2 and 3 and then check your work? So 2 you should have gotten negative 1 for, and 3 you should have gotten -3 as a solution. And then as a reminder, whenever you're graphing in two variables, you can always, if you forget how to graph something, because we're going to go over the efficient ways of graphing linear equations, the efficient ways of graphing quadratic functions, the efficient ways of graphing exponential and logs and trig, and that's really the study of Algebra 2, is taking all of the concepts and basic understanding of functions and expanding your family of functions. So we will apply what we know from Algebra 1 and what we're reviewing right now to more advanced and complex functions. But one thing that I always want you to keep in mind is if you forget all the different strategies for graphing, you always have this in the back of your mind as this is something that I know I can do if I get stuck. You can construct a table of values. Next, you can graph the solutions and recognize to see if you get some sort of pattern from it, and then connect the points to make a line or curve from it. But always, table of values is what I recommend if you don't remember the fancy strategies that we go over for each particular function family. And then we'll now talk about briefly 2.2 direct variation, because direct variation is an example of a linear function, and the relationship that you see in x and y show a direct variation when we are in a linear equation, or when we're discussing linear equations, you'll notice a direct variation between x and y. So two variables, x and y, show direct variation provided you have this relationship where y equals k times x. Okay, that should look familiar to us, and this is provided y equals k times x and that k does not equal 0, because if k equals 0, then we would have y equals 0, which is no longer a direct variation. So the k takes on a special meaning. It's called our constant of variation. We can always solve for that constant of variation by dividing by x. So if you notice that y equals x is constant, constant means that it's the same number each time. So we'll put in parentheses k. We would then make that conclusion that it's direct variation. So if I can show that y over x is a constant value, then my conclusion is that the relation is one of direct variation. So if you take a look at A, you have a table of values, and the question will say, does this relation show a direct variation? What we would need to show is that y over x on each one of these ordered pairs is indeed a constant value. So when I put -21 over 3, I get -7. When I put -14 over 2, I get -7. And then finally -7 over 1, we do get -7. So our conclusion, this is the therefore symbol in math, our conclusion is that this is direct variation. And they might ask you to find the constant of variation, which we just did. The constant of variation is -7. And then further, they would ask, what is the equation for this direct variation? We would then take the -7 and put it in front of our x, as you see it in the original equation. So y equals -7x. Let's do one more example. So I'll switch to color so you know that this is the start of the next example. So example number 2, let's do a table of values. And this time, after I put in the ordered pairs, -2, 4, -1, 2, 1, -2, I'd like you to find the constant of variation and also write the equation of this relation that is a direct variation, and I will tell you it is a direct variation. If you can fill out in the fill in the blank what the constant of variation is in play pause it, and then also what your direct variation equation is. So like in the previous example, k equals -7 was the constant. This was the equation. And then I will grade that and see that it is, to see if you get the idea behind it. If you're having trouble with it, feel free to email me. So one thing I do want to point out is that you should notice I had mentioned something about that direct variation equations are related to linear equations. I want you to take that leap, and what do you think the relationship is between direct variation, and why is it an example of linear equations? So if you read the last question that we have here, what do you notice about the equation of a direct variation equation? So y equals k times x. Well, if we below that write y equals mx plus b, what would the k represent in our linear equation? K represents our slope in our linear equation. What's the y-intercept of our direct variation equation? Okay, you should notice that the y-intercept is the origin, or 0, 0. We write our x and y-intercepts as a coordinate point. So it is a more specific example of a type of a linear equation. It's a pattern that we notice, and then we tie it to this concept of a direct variation, but it is